In the last video, we proved that the path of our planet was going to be in the XY plane. So I've kept up this picture, which gives us our frame of reference here in 3 space, but I've also added a picture of just the XY plane. Now, we are working on the XY plane in 3 space, so for this picture, the Z-axis would just be pointing straight out from the board. I'm looking on the XY plane because that's where everything's happening. Okay. And at every moment in time, we're going to have an R vector, that's our position vector, that's pointing from the sun to the location of the planet. A vector is always just determined by its magnitude and its direction. So what I've done is I've introduced this unit vector here, which points in the correct direction of R, and then I've said that the vector R, the position vector, is just the distance of the planet from the sun, which would be the magnitude of R, times that unit vector. But I know, because I'm working in the XY plane, that I can describe that unit vector in terms of the angle that we make with the positive x-axis. If we were just in 2 space, it would just be cosine theta, sine theta. Now, we're on the XY plane in 3 space, so we've got a z component of 0. So the unit vector u is cosine theta, sine theta, 0. Now notice what this does. We've said that our goal is going to be to show that we're getting a conic section and to describe that in polar coordinates. Well, there's my r and there's my theta. So I'm introducing those polar coordinates in my description of this position vector. What we're going to do as we work through the videos is we're basically going to characterize a bunch of vectors a bunch of different ways. I'm going to start with the acceleration vector in this video, and I'm going to try to describe the acceleration vector. Okay. Now, I'm going to do that just using some things that we know. So, for example, we know that force is mass times acceleration. But we also have a property about the force, because the gravitational force field is what we call an inverse square field. We'll actually be studying those in chapter 16. For now, what you need to know is that the magnitude of the force is inversely proportional to the distance between the sun and the planet. So we can write that this way. The magnitude of the force is going to be some fraction where what's on the bottom is the distance between the sun and the planet squared. What's on top is going to be a constant. And that constant is determined by 3 things: the universal gravitational constant, the mass of the sun, and then the mass of the planet. Okay, so that's the magnitude of this force, but I also know the direction in which the gravitational force field acts, because it's an attractive force. So if we've got the sun here at the origin, the force is acting towards the origin, pointing from the planet towards the origin. Well, u, this unit vector that we just introduced, points in exactly the opposite direction. It points from the sun towards the planet. So the direction of gravity is exactly the opposite of the direction of the position function, which is the same as the direction of this unit vector. So if I put those pieces together, I can say that force, which I know is mass times acceleration by Newton's law, I know that I can take the magnitude, gmm over r squared, and use that to scale the opposite of u, the unit vector that points in the right direction. And what I'm going to do here is I'm just going to solve for the acceleration. So if I solve for acceleration, I want to divide through by m. Now, I'm just working with this part right here. I'm going to just ignore the f. But if I do that, I'm going to get the acceleration is, and I'm going to just bump this negative sign and put it with the rest of the scalars, negative gm over r squared times u. That's a characterization of the acceleration. Now, it's not immediately obvious why that's a useful characterization. I will point out that it gets r, and because u is defined in terms of theta, the angle that we make with the positive x-axis, it does get r and theta into our description of the acceleration, and that's going to be helpful when we're trying to ultimately write everything in polar coordinates. Okay, but again, your job here isn't to understand why I wanted to describe acceleration that way, only to follow that, yes, that is correct. We can describe acceleration that way. That is true. Why it is useful is not yet clear, but we hope it will become clear soon.